properties. So now we're skipping chapter 4. We did it already, right? And now we're in chapter 5, which is properties. Well, chapter 5 is actually, it's the running head is a little screwed up there. So system properties and first and second order response we're going to talk about for the remainder of the term in this last chapter. So system properties we talk about in this properties of LTI systems. Then we're going to talk about stability, and then we're going to do first and second order system responses, and that's it. The rest of the semester. So it's good fun. 5.1 properties of LTI systems. From the principle of superposition, linear time invariant, or LTI, system responses to both initial conditions and non-zero forcing can be obtained by summing the free and forced responses. Okay? So this is the free response. Let's remember what that is. That's the response of the system with inputs all 0. So inputs 0, but initial conditions not equal to 0. Okay, so whatever they are. I mean, if they're equal to 0 too, then nothing happens, right? If you have no inputs and no non-zero initial conditions, the system just sits there. Pretty boring. So this is the free response, which is you set it to some non-zero initial condition and you let it go and it happens. Okay. The forced response is exactly the opposite. U is not equal to 0, input's not equal to 0, and initial condition is equal to 0. So we set the initial condition is equal to 0. The inputs are not equal to 0. So the total response is actually just the sum of those two. So we can do these two separately, which is really convenient to do. Okay. So oftentimes we will actually, for certain types of systems, first order, second order systems, for instance, we will find the free response for certain initial conditions, and we'll have a form of it all set up. And then similarly, we'll have the forced version over here. And then depending on your situation, you can mash them up together according to what's going on. Maybe you just have an initial condition and you have no forcing. Or maybe you just have forcing and no initial condition. You can use these. And so we come up with tables that are really nice for sort of constructing these solutions from free and forced responses relatively quickly. So we don't have to do the entire analysis every time. So for first and second order systems especially, we can look up the solutions in a table oftentimes instead of having to go through the whole solution every time, which is great. Because I know that you guys don't really like 3-4 page differential equation solutions. So this can be really powerful, really helpful. Moreover, superposition. So superposition says this about free and forced response. So that's one really nice thing. So you can separate out the free response from the forced response. Awesome. Superposition also says that any linear combination of inputs yields a corresponding linear combination of outputs. That is, we can find the response of a system to each input separately, then linearly combine, which means scale and sum, the results according to the original linear combination. That is, so mathematically, for inputs u1 and u2 and constants a1 and a2, a forcing function, where am I here? There we go. A forcing function, f of t. So remember what the forcing function is. It's the right-hand side of the input-output differential equation, right? The forcing function is a1 u1 plus a2 u2. So let's say this was your forcing function. It would yield an output equals a1 times y1 of t plus a2 times y2 of t. y1 is the output of the system to input u1. So u1 gave y1, u2 gave y2, and if we wanted to know what the response of the system was to some linear combination of u1 and u2 like this, all we need to do is take the linear combination of these outputs that we already have. So this is another really powerful principle because it allows us to say, oh, you have an input that is composed of a bunch of different functions. We can solve for each of these separately. Okay, so we can solve for the response separately and then combine them later. That's great because when you do method of undetermined coefficients, then you can break it down to just one input. So like, oh, you have a sinusoidal input and you have like a constant offset in your input. No problem. We'll find the solution to the sinusoidal one and we'll find the solution to the constant one separately, and then we'll combine them. Now, this is powerful from the sense of, oh, you can break your problem down into smaller parts. But it's especially powerful if you want to be lazy, okay? So, if you want to be lazy and you don't want to solve out for the whole solution every time, you can look up a table where it has, oh, the response of a system to a step input of a, say, we have a second order system. A second order system has a response to a step input, that's this. Forced response, that's this. Oh, it also has a response to a sinusoidal input is this. We can then compose them. In any given situation, we might have multiple of those inputs going in. No problem. We don't have to go back to square one and solve the whole thing over again. We can just use the solution for the step input separately from the solution to the sinusoidal input, and then just add up the solutions. So this is really helpful, so we don't have to go through a whole lot of analysis every time we encounter what ends up being often really common problems. So first and second order systems come up all the time, okay? It's not just in school. Like in the real world, first and second order systems come up all the time, mostly because, well, sort of could be some deep reasons why that is, but we can often model a system as first or second order, okay? And actually higher order systems just look like combinations of first and second order systems oftentimes, as long as they're not nonlinear, in which case you're totally screwed. Really good on the editing today, I have to say. Okay, so we're almost done. So this powerful principle of superposition, so it applies, or let's remember, only to linear time invariant systems. So if your parameter, like your mass, changes throughout the time the problem is effective, this doesn't necessarily apply. If it's nonlinear system, like if you have a nonlinear resistor or something like that, or a spring that's nonlinear, you can't use this principle of superposition. But for linear systems that don't have parameters that are changing through time, or at least for systems that can be approximated as behaving that way for some analysis, we can use this powerful principle. So it allows us to construct solutions to complex forcing functions by decomposing the problem. It also allows us to make extensive use of existing solutions to common inputs. And this is where, so chapter, I think it's 9 of the System Dynamics textbook by Rowell and Wormley, it has tables of solutions to certain inputs. That's really helpful. You don't have to solve everything out. So there's one more LTI system property worth noting here. So there are two aspects to it. So let a system have input U1 and corresponding output Y1. If the system is then given input U2, which is just the time derivative of U1. So if you differentiate the input, the corresponding output Y2 t equals just the time derivative of the output that you got from U1. So U1 gave Y1, and if we say, oh, instead of putting in U1, let's take the time derivative of U1 and put it in. You don't have to resolve the problem. All you have to do is take the time derivative of the solution you already have. So that's a nice property. Once again, this is a nice like sort of lazy solution technique, right? Don't have to actually do stuff. We can just sit back and say, oh, by superposition, we don't have to work. Okay, so similarly, if the same system is then given input U3, which instead of being the derivative is the integral of U1, the corresponding output is y3 of t equals, you guessed it, the integral of y1. And we're using tau here, not to mean time constant, but to just be a dummy variable for integration, right? Okay. That's it. So if you integrate the input, you integrate the output. Or if you differentiate the input, you differentiate the output. If you multiply the input by 4, you multiply the output by 4. If you add 2 inputs, you just add 2 outputs. It's like everything you would like it to be. It's true for a linear time invariant system. All right, guys. I'll see you guys Friday.